Figure 6 shows a sketch of the curve C with the parametric equations x equals 8 cos cubed theta, y equals sine squared theta, where theta is between 0 and pi over 2. Given that the point P lies on C and has parameter theta equals pi over 3, find the coordinates of P. So nice and simple to begin with, we're just substituting our theta in to our x and y equation. So x equals 8 times cos of pi over 3 cubed gives 1. Y equals 6 times sine of pi over 3 squared gives 4.5. So the point P has got the coordinate 1, 4.5. Part B. We're told that the line L is normal to the curve at P, and we need to show its equation is y equals x plus 3.5. So it's normal to the curve, so we know that it's perpendicular to the tangent at point P. So L is perpendicular to the tangent. So if I can work out the gradient of the tangent, then I can do the negative reciprocal. So let's get our gradient function first of all, and we'll use the formula dy by d theta divided by dx by d theta. So we need to differentiate our x and our y functions. To do this, it is helpful to write in this form, just to help with the chain rule. So I'm going to rewrite the x as 8 cos theta cubed. That's going to be helpful. In fact, let me move that over here. So that's going to be helpful for me to differentiate, because I can just see the chain rule more clearly now. So I'm going to multiply by the 3. I'm differentiating the outside function, the power part first. So 8 times 3 is 24. Take 1 away from the power. And then I have to multiply by the derivative of the inside. The derivative of cos is minus sine. So that's my dx by d theta. Doing the similar thing with the y function, so I'm going to write that as 6 sine theta all squared. So differentiating the outside function first, which is the squared. So I will have the 6 times the 2, which is 12. Take 1 away from the squared function, so that's just 1. And now differentiating the sine, I get cos. So my dy by d theta is 12 sine theta cos theta, and my dx by d theta is minus 24 cos squared theta sine theta. Now we can see that that's going to simplify quite a lot. See, the 12 and the 24 will simplify just to be 1/2. Or rather minus 1/2 because of the minus 24 on the bottom. The sine thetas cancel out. The cos theta will cancel with one of those cos thetas. So I've just got a single cos theta on the denominator. So this is my gradient function. I can now say at point P, I already know that theta is pi over 3 at that point, so if I substitute that in, dy by dx is minus 1 over 2 times cos pi over 3, which is minus 1. Therefore, the normal gradient is going to be the negative reciprocal of that, so plus 1. I can now do y equals mx plus c. I know the gradient is 1, and I know it passes through point P, which is 1, 4.5. So substituting that coordinate in, I see that C is 3.5. Therefore, the equation of my normal is 1x plus 3.5, which was what we needed to show. The finite region S, shown shaded in figure 6, is bounded by the curve C and the line L, the y-axis and the x-axis. Show the area of S is given by this expression. So, first thing I'm going to do is I'm going to draw a vertical line at point P, because I can see that shape S is made up of two distinct different areas. We've got part A and part B. Part A is a trapezium and part B is the area underneath the curve. A here is a nice trapezium which we can find easily. We know how to work out the area of a trapezium. And part B is going to be the slightly trickier part. We'll have to use integration to get this. So this is a show that question. So area or total area equals A plus B. So let's do the trapezium first of all. So it's trapezium. So I know this is going to be half A plus B times H, where A and B are the two parallel sides and H is the height between them. So the two parallel sides, well, this is one of them and this is the other one. Well, in the previous part of the question, we found that the y-intercept of our normal was 3.5. So therefore we know that our first height there is 3.5. And we know the y-coordinate of point P was 4.5. So we know that A and B are 3.5 and 4.5. H, the height between them, well, that's going to be the same as the x-coordinate of point P, which was 1. So half times 3.5 plus 4.5 is 4. So that's the area of A. Next, for B, it's going to be slightly trickier. We need to integrate here. And we need to be integrating between our lower limit of x, which is 1, and our upper limit of x, which is this. We're not quite sure what that's going to be yet. So we're going to have to figure that out. The one thing we know at this point here is we know that y is equal to 0 at this point. So if we take our y equation, that means that 6 sine squared theta is going to equal 0. So therefore sine theta has to equal 0. So therefore theta is going to have to equal 0. If theta equals 0 at this point, then we know we can substitute that into our x-coordinate. So x equals 8 times cos 0 cubed, which is 8. So we're integrating between 1 and 8 of y with respect to x. But obviously in this case we are going to be integrating with respect to theta and not with respect to x. So we need to change this. We need our limits to be in terms of theta, not x. So when x equals 1, our lower limit, theta was pi over 3. We already showed that in a previous part of the question. And when x equals 8, again we just showed that theta was 0. So our upper limit is 0. Right, so that's our limits sorted. Now let's do the inside. The y we know is 6 sine squared theta. The dx by d theta, we worked this out a couple of moments ago, was minus 24 cos squared theta sine theta. Now tidying this up, this minus here means that I can flip the limits the other way around, so I have the smaller number at the bottom and the bigger number at the top, so that's useful. What else have we got here? We've got the 6 times the 24, which is 144. So I can take that outside. And then I'm left with the sine squared times sine, which is sine cubed, times cos squared. But that doesn't quite look like what I was expected to show. I actually quite wanted to keep this sine theta, and I don't want to have this, so I wanted to keep this sine theta here, but I don't want this sine squared here. So actually that step I've just done there, I probably didn't want to do that. So instead of me doing that, instead of me rewriting the sine squared times sine as sine cubed, instead I'm going to rewrite this sine squared as 1 minus cos squared. And I'm going to keep this sine theta. I think that's going to get me closer to the way it wants me to write the answer. Even though this looks much more complicated, I would prefer to have done what I just wrote down. I would have preferred to have written the sine cubed. But I think this will get me to the answer they want me to write, which I'm assuming is going to help me in the long run. So just to repeat that, because I don't think I've explained that very well. I looked at my answer here. I've got sine theta cos squared theta minus sine theta cos to the power 4. The sine is appearing as a single sine. There's no sine squareds or sine cubes or anything like that. So I've decided to keep this sine theta exactly the same, keep it separate, and I'm going to turn this sine squared theta into a 1 minus cos squared theta. Right, let's expand this back out. So I've got 1 times cos squared times sine. So that's going to be sine theta cos squared theta. And then I've got the minus cos squared times cos squared, so that's minus cos to the power 4 times sine. So there we go, and that seems to match up with what I needed now. So therefore my total is a plus b, so 4 plus 144 lots of this integral. That's part C. And finally part D, hence. So hence, this must be the key thing about why they told me to write my answer like this. Hence, by integration, find the exact area of S. So I'm going to rewrite this integral. So I've got the 4 plus 144 times the integral of 0 from pi over 2, pi over 3, sorry. And I'm actually going to write this in a slightly different way. I've got the sine theta times cos theta squared minus sine theta times cos theta to the power 4. And the reason I'm going to write it like that is because I'm going to use the spotting a derivative trick here. That's why they've told us to write it like this in part C. This is easy to integrate if you can spot this derivative. Let me just quickly remind you what I mean by spotting a derivative. I mean a situation where you are asked to integrate something, a function like this, where you have the derivative of the function on the inside on the outside. So if I've got some function on the inside of a power and its derivative on the outside. That's really good because it means you can completely ignore the derivative and then just add 1 to the power and divide by the power, like you normally would. So this is the trick I'm going to use here. I'm going to look at this integral really carefully. Let me just copy this bit down first of all. Right, and I'm looking at the cos x, or cos theta rather, on the inside there, and that differentiates to be minus sine theta, which is not exactly what I've got there at the moment, but that's fine. I can make it become a minus as long as I introduce another minus there. Let me just repeat that. I looked at the cos theta on the inside here, and I know that differentiates to be minus sine theta. I didn't have a minus, so I introduced one, as long as I've got this extra minus at the front. That's really good to do because it means I can completely ignore this derivative. I'll still have this minus here. And now I can add 1 to the power and divide by the new power. Similarly, with the second integral, I've got a cos theta on the inside here. I know the derivative of that is minus sine, which I've already got here, which is great. So that means I can completely ignore that derivative at the front there. Then add 1 to the power and divide by the new power. And that's it. That's been integrated now. That's why they told us to write it in that form, to make it easy for us to integrate. I'm not saying it's still super easy, but it's certainly a lot easier than it was before when we had the sine cubed cos squared. All we need to do now is substitute the limits in. So minus 1/3 cos pi over 3 cubed plus 1/5 cos pi over 3 to the power 5. So that's substituting the pi over 3 in. Now substituting the 0 in. We will work all that out. We will then times it by 144. So work all that out, times it by 144, add the 4, and our final answer is 181/10.